Designed by nature, Biomimetics. One cloudless midsummer day, biologist Andrew Parker knelt in the baking red sun of an Australian desert and gently placed the right back leg of a thorny devil into a dish of water. The thorny devil, a small lizard that has learned to survive in the extreme heat of the Australian desert, has a secret that fascinated Parker. "Look, look," he exclaimed. "Its back is completely drenched." Sure enough, in less than a minute, water from the dish had travelled up the lizard's leg, across its skin, and into its mouth. It was, in essence, drinking through its foot. The thorny devil can also do this when standing on wet sand, a vital competitive advantage in the desert. Parker had come here to solve the riddle of how it does this, not from purely biological interest, but with a specific purpose in mind: to make a device to help people collect water in the desert. From natural wonder to useful tool. Parker is a leading scientist in the field of biomimetics, applying designs from nature to solve problems in engineering, materials science, medicine, and other fields. His studies of the body coverings of butterflies and beetles have led to brighter screens for cell phones. He has even drawn inspiration from nature's past. While visiting a museum in Poland, he noticed a 45-million-year-old fly trapped in amber and observed how the shape of its eye's surface reduced light reflection. This shape is now being used in solar panels to make them more efficient. As part of the next phase in his plan to create a water collection device inspired by the lizard, Parker sent his observations to Michael Rubner and Robert Cohen, two colleagues at the Massachusetts Institute of Technology. Parker is full of enthusiasm about the many possibilities of biomimetics. Rubner and Cohen, on the other hand, are much more practical. They focus on the ideas that have a chance of being applied successfully. This combination of biological insight and engineering pragmatism is vital to success in biomimetics, and it has led to several promising technologies. Though Rubner and Cohen are certainly impressed by biological structures, they consider nature just a starting point for innovation. Cohen says, "The natural structure provides a clue to what is useful, but maybe you can do it better." They consider a biomimetics project a success only if it has the potential to make a useful tool for people. "Looking at pretty structures in nature is not sufficient," says Cohen. "What I want to know is, can we actually transform these structures into something with true utility in the real world?" Unlocking nature's secrets. The work of Parker, Rubner, and Cohen is only one part of a growing global biomimetics movement. Scientists around the world are studying and trying to copy a wide variety of nature's design secrets. In the United States, researchers are looking at the shape of humpback whale fins in order to help wind turbines generate more electric energy. The shape of the body of a certain fish has inspired designers at Mercedes-Benz to develop a more efficient car design. By analyzing how termites keep their large mounds at the right temperature and humidity, architects in Zimbabwe have built more comfortable buildings. And in Japan, medical researchers have developed a painless needle that is similar in shape to the proboscis of a mosquito. The bio-inspired robot. Potentially, one of the most useful applications of biomimetics is the robot. Robots can perform tasks that might be too boring or dangerous for humans, but they can be extremely difficult to build. Professor Ronald Fearing of the University of California is creating a tiny robot fly that can be used in surveillance or rescue operations. Fearing's fly is a simplified copy of the real thing. Some things are just too mysterious and complicated to be able to replicate, he says. It will still be years before his robot fly can perform anything like an actual fly, but Fearing is confident that over time, he will close the gap between nature and human engineering. At Stanford University in California, Mark Kutkotsky is working on a robot gecko. Kutkotsky studied the extremely small structures on the tiny lizard's feet that allow it to run up and down vertical walls. He applied what he learned to create StickyBot, a robot that can walk up and down smooth vertical surfaces. The US military, which funds the project, hopes that one day StickyBot will be able to climb up a building and stay there for days, monitoring the area below. Kutkoski believes there will be a range of non-military uses as well. I'm trying to get robots to go places where they've never gone before, he says. For now, StickyBot can only climb extremely smooth surfaces, unlike a real gecko, which can run up just about any surface very quickly. Despite the promise of the field and the brilliant people who work in it, biomimetics has led to surprisingly few business successes. Perhaps only one product has become truly famous: Velcro. The material was invented in 1948 by Swiss engineer Georges de Mestral, who copied the way seeds called cockleburs stuck to his dog's fur. Some blame industry, whose short-term expectations about how soon a project should be completed and become profitable conflict with the time-consuming nature of biomimetics research. But the main reason biomimetics hasn't yet been a business success is that nature is incredibly complex. Nonetheless, the gap with nature is gradually closing. Researchers are using more powerful microscopes, high-speed computers, and other new technologies to learn more from nature. A growing number of biomimetic materials are being produced. And although the field of biomimetics has yet to become a very successful commercial industry, it has already developed into a powerful tool for understanding nature's secrets. More nature-inspired innovations. A type of glass has been created that draws inspiration from spider webs. Birds can see the ultraviolet reflective strands in the glass and thus avoid flying into it. Water does not stick to a lotus leaf because of its surface structure. Copying this process, one company has developed a water-repelling sealant that can be sprayed on surfaces. Swimmers can now swim faster because of new suits that mimic the design of shark skin. This design is also used to reduce friction on ships, submarines, and airplanes. High-speed trains have long, beak-shaped noses, modeled after the kingfisher bird. This reduces noise and allows the train to travel much faster. A new fan on the market is based on the spiral shape seen in tornadoes and whirlpools. The fan cools the air more efficiently than traditional fans.